This is part one of two on the lecture on samples and generalizations drawn from chapter 6 in your textbook. All of the research studies that we've highlighted in the chapters up until this point, whether it's Kelly MacDonald's research on neuromyths, the Dunn research on prosocial spending and happiness, or even Stanley Milgram's obedience study, each of them had a concern as to what population their findings could be generalized to with high validity, reliability, and accuracy. So in all these different fields of research, we always have to think about which population we are trying to eventually be able to draw conclusions about. So the process of identifying your population and then how do you draw a sample from that population is what we're going to focus on for these two sections to this lecture. So ultimately, what we want to do is, it'd be great if we could sample the entire population, right? In some cases, if you had the resources, if it was feasible, if it was practical, then it would be nice to go out and ask questions of or do your experiment on every single person in the population. But as you can imagine, that's extremely difficult and often impossible to do. It's just not practical, or it may not even be feasible to get every single member of a population, even if it's a very precise, narrow one. So we always have to work with a sample that we've drawn from a larger population. That's always one of the things we're trying to do effectively in our scientific method. So the purpose of this process of sampling is to generate a subset that's representative of the whole set, as far as most of its significant properties or characteristics are involved. The idea is that this smaller sample is what we call representative of the larger population. Now, as you can imagine, the first step in that is to identify what the population is. Which population are you studying? This is not always as simple as it seems. It's not always so general in psychology that we're studying all human beings. I mean, there are some fields of research, some programs of research that are trying to generalize as much as possible to human beings. But a lot of times we have an idea of a subpopulation besides everyone that we're interested in. So the first thing you have to do is identify which population you're interested in. This can be the entire collection of people, animals, or things, whatever the population is of interest that you're studying. In psychology, a lot of the time what we're studying is human beings, but sometimes we're studying white mice or primates of some kind, or some other sort of stand-in for human beings. And sometimes we're studying specific things, but ultimately in psychology we're typically talking about a collection of people that fit certain characteristics. So in your study, at the very early stages of developing a research design, you need to state clearly which population is actually being studied. So it's not fair to assume that research applies to everybody. For example, one of the things we see a lot in psychology is the convenience of utilizing undergraduate psychology students as a research population. That's because at most universities, traditionally, psychology students are encouraged to volunteer, to take part in research studies. That's a win-win for both sides of that equation. Ultimately, the researchers have subjects and they're able to draw larger samples to conduct their research, but also it allows the students to have an opportunity to be on sort of the participant end of research. So it's been a long-standing sort of mutually beneficial relationship. But as you can imagine, if the only people that you're studying are undergraduate college students, or even more specifically, psychology students that are undergraduates, that's the population that you're looking at. And if you want to generalize to a larger population, you have to make some points of argument along the way to come to that conclusion. So typically, you can't just say, oh, well, this applies to all people if you only studied or only sampled from a singular population, like, for example, college students. So you must know if your findings can be safely generalized to other populations. Once you've figured out what your population is, right? Once you know the entire collection of people, animals, things, etc., then you have to utilize a procedure for sampling from that population. And it's not as simple as catch can in most cases. The idea here is that you want to do this in a systematic way that provides you with a sample that largely looks like the population in many important ways. So there's a procedure we have to then utilize so that we're hopefully getting what's called generalizability. This is done by getting a representative sample from the population that can then be generalized back to the whole. We sometimes use some terminology within this. We sometimes call The individual members of the population whose characteristics are to be measured, the actual people that get pulled into your sample, we'll call them cases or elements. Elements is a more general scientific term that can be applied to other types of populations besides people. But ultimately, we have this larger population. We then have this sample that we pull from the larger population, and within that sample, we might refer to the individuals as elements or cases. So if we wanted to study students in an identified school, we would need to have, a full listing of all the students that are in that school. That might be where we start. That's the population that we're studying. So let's move on to how we go about that process. So these are the important components of a sample that's drawn from a population. We start with something, if we can, called a sampling frame. A sampling frame is essentially a list of every element, every case, every unit within that population. If I'm studying a school example, like I mentioned before, that would be a list from the registrar that has every single student's name on it. That could be my sampling frame. If I'm trying to randomly select from Virginia Tech psychology students, maybe the registrar would provide me with a list of all the psychology majors in the department or all the people that are enrolled in introductory psychology or something to that effect. But a sampling frame is basically just a list of every individual unit within that population. The sampling unit then is the set of students from the list that have a particular distinction. I might not want to study every student on that list. I might have something specific. I might only be interested in freshmen, for example, versus upperclassmen. I may only be interested in men or women in my study. I may be only interested in students of color for something that I'm studying that has a sociological impact associated with that. I may only be interested in students that have a history of some particular illness in the past or some designation. So there's a smaller unit within there sometimes that we distinguish with a characteristic. The example here, students with red hair, right? Just something specific about those individuals within the larger population. The goal then is to pull a representative sample from the larger population. Representative is the key word here. You want the sample to look like the larger population. It needs to share with that population the same distribution of characteristics, for example. So that's why we sometimes have to know distinct things about the population, because we want to make sure that the sample we pull looks like the population. You must know exactly what population you are studying to know if your sample is representative, right? You have to know details about what the population is in order to know if the sample you draw is representative. And you have to be precise and specific. So for example, if I use the term adult Americans, that would essentially be roughly, U.S. residents who are 21 years or older, 18 years or older, however you're drawing that distinction. That's a different population than, say, adult English as first language speaker Americans, right? So if you want your sample to look like your population, then you need to know the characteristics of the population to determine whether or not it's representative. This is a little figure from your book. This is Exhibit 6.2 from the chapter. This shows you an example of a population. So the larger circle up here is our population, right? And what you're seeing is these smiley faces and happy faces are representing individuals that are satisfied or unsatisfied with some procedure, some service they've received. It's really not important for the purposes of this demonstration. But as you can see, we have 1, 2, 3, 4, 5 people that are satisfied, and 4, 5, 6, 7, 8, 9, 10 that are unsatisfied. So we know that within the population, we have 33% that are satisfied. Now, I can go in and I can randomly select from that population, right? And these are two possible samples that I may just randomly end up with. This one has a disproportionate number of satisfied people and a underrepresented or a disproportionate number of unsatisfied people. In that meaning, it does not look like the larger population. It is not. It is an unrepresentative or non-representative sample. In this case, you would assume, based on this sample, that in the larger population, you've got 2/3 of people that are satisfied, when in fact it's 1/3. The second sample here on the left shows that it is representative. It has the same proportion, in this case 2 out of 6 versus 5 out of 15, but it's still at 33% representative sample. 33% satisfied, excuse me. So it does represent, in this sample, the larger population. And this is just a visual to help you kind of grasp the idea of what we mean. Now, keep in mind, the only characteristic that's being represented here is satisfaction, because that's what we're studying in this case. That's the sort of that's the sampling unit. That's the thing we want to know about the population, so we can know whether or not the sample we draw is in fact representative. So once we've drawn a sample from our population, we want to know whether or not it is generalizable, right? If it can be generalized back to the larger population. That's a goal, is that your sample is representative of the population, and that means that it looks like it. It shares the same distributions of characteristics. Unfortunately, as is the case with virtually every aspect of science, there is always room for the introduction of error. There are always problems that can be added to this issue. In this case, what we're looking at is what we call sampling error, and this is the difference between the characteristics in the sample and the characteristics of the population. Going back to that previous figure, the unrepresentative sample on the right has a lot of sampling error, right? And it just happens sometimes randomly. We try to minimize sampling error as much as we can, but it can never be entirely eliminated. There is always going to be some degree. You're never going to get a sample that looks exactly like the population or represents it perfectly, and the reason why is that it does not contain all the members of the population, right? Some people are being left out, and it's very uncommon for you to end up with a sample that looks exactly like the population. There's just a question of it being good enough, close enough to draw conclusions and generalize back to the larger population. But as you can imagine from this thinking, the larger the sampling error, the less representative the sample. In the previous figure we looked at, it's 33% off, right? It's a huge difference. It does not really tell you what the actual population looks like. We also are sometimes concerned about cross-population generalizability. Not only can I compare my results from my sample to the population that I drew it from, but can it represent other populations, often larger populations? And we call this concept external validity. The population to which the generalizations can be made is sometimes termed the target population. This is sort of the population from which you drew your sample. This is the set of elements that are different from the total, but you do draw a representative sample. In some cases, though, we don't just want to be able to generalize back to our target population, but to a larger or another population as a whole. And so the validity of cross-population generalization is tested by replicating the same study in different settings, meaning you go out and draw from a different group of people, a different population. Do you find similar findings? Do you get similar results? The more that happens, the more it's replicated, the more we say that the study or the theory has high external validity. It's very generalizable across populations. So one of the things we have to know when we get started is we have to assess the diversity of the population. If you think about this for a minute, if every unit within the population is identical, if there's no variability, then you don't need to sample, right? Essentially, we assume that with human beings there's diversity of characteristics, right? And we're not all the same. We're unique in our own ways, and we share certain things, but we're also different in a number of ways. So if you're sampling from something that is completely identical, that every single unit is exactly the same as the other, there's no real reason to worry about how you sample, right? In fact, you could think about this logically. You could study one individual from that population, and you would be able to make generalizable claims about the larger population. This does not happen in human beings, but in certain types of research it does. A single atomic particle of one particular element is identical to every other particle of that element, okay? But human beings, of course, are a lot more complex than atomic particles in that sense. There is often a risk of assumption across studies that people are all the same, and we have to be very careful about that. Let's talk about Milgram's study on obedience and how it relates to this. He came to the conclusion that people are very obedient, and that's not because of this small group of 40 males from New Haven, Connecticut that he examined. What happened was, remember that Milgram was actually kind of surprised by his outcome. His original intent was Americans are different than Germans, right? I'm going to study Americans this way. I'm going to find that many of them refuse to go on with the study. They're going to show a resistance to authority or a lack of obedience to authority. And then I'm going to go conduct the study on a German sample, and I'm going to show this cultural distinction. But in fact, he was blown away by how compliant, how obedient the sample of 40 males from New Haven was. And as you can imagine, Milgram and other researchers were quick to want to go out and say, well, is there something unique about these 40 people? It's a relatively small sample, right? What they found was that the study's been replicated many, many, many times with lots of different types of populations and samples, and they've gotten similar results. They did find that there were some distinctions. Some subjects were less likely to react as obediently, but the value of that initial research and the many replications that happened thereafter gives us a lot of insight into people's obedience. It also helped us to understand things and types of people and conditions to which you couldn't generalize as much. Remember, we talked about how you can change the distance between the authority figure and the subject. You can change the distance and the connection and the relationship between the person being shocked, deceitfully, not actually shocked, but ostensibly being shocked, and the person who's doing the shocking, the subject. You can change that, and you change the levels of obedience. We talked about the example of doing it over the phone or doing it over the computer. So there are, some variability where you can't generalize fully, but that replication across populations showed us that you can to a certain extent. Nevertheless, it's important to remember, as I said, that people are too diverse to be considered as identical units. And it's important that experimental results are replicated with different subjects in different settings with samples drawn from different populations if we want to be able to talk about the generalizability of those findings and of the theory as a whole. So I made a comment earlier about how, well, it's very rare that we can ever conduct, sample every single individual from the population. If we're able to do that in a perfect world, that's not a bad thing. And we do have a term for this. We call it a census, right? I'm sure many of you are familiar with the U.S. Census. We just conducted one in 2020. It's done for a number of factors, including representation in Congress, but a lot of other things as well. And a census is essentially where you go out and you survey or you conduct an experiment on every single unit of the population, on every single individual. So that's where you avoid the problem of sampling because you actually study the entire population. And a census is where you obtain this information through responses from all available members of an entire population. However, as you can imagine, it's not perfect and it's not possible to get everybody. For a variety of reasons. The first of which is cost, not just in terms of money, but in time and resources. If you are trying to generalize to a larger population, to all Americans, all adult Americans, all college students, whatever, that's just not possible. To go out and conduct your study on every single member of the population. So it may be impossible, it may be impractical, it may be too expensive. Even the census is not perfect by any means, right? Especially with COVID, we saw a lot of problems associated with the census. There's also some sociocultural issues associated with the census. Some people are reluctant to talk to census takers for a variety of reasons, including people like undocumented immigrants, for example. So the 2010 census, we don't have all the data on the 2020 yet. They do it every 10 years in the United States. It's written into the Constitution. So in 2010, the census, which is, pretty much a simple survey of an attempt to do a survey of every, American citizen, it cost $5 billion to conduct the 2010 census. That's nothing to scoff at. That's certainly way beyond the scope of the type of research funding psychologists get for the most part, right? So $5 billion is nothing to scoff at. In terms of a federal budget, it's a drop in the bucket, but it's a lot of money no matter what, however you slice it. And keep in mind that that $5 billion census found that 28% of Americans still didn't return the mailed census. Okay, 3.8 million temporary workers were hired to contact the missing respondents. That's a lot of people. That's a lot of money. So this demonstrates really kind of, I think, poignantly why it's so important to utilize a sample, especially in surveys. It's just impossible to get a response from everybody. And even if you can get it, it's often extremely impractical or very expensive. There are a few methods for sampling a population, a few ways in which we can go out and draw a sample from a larger population. And you can generally distinguish them into probability and non-probability methods. Probability is always the preferred method because it tends to give you more confidence in that sample being representative of the larger population. But I am going to talk a little bit about non-probability sampling methods first. So what makes it a non-probability sampling method is that I do not know in advance the likelihood of selecting each element. So I'm going to explain this more as we get into the slide on probability sampling methods, but for a moment, if I have a good sampling frame, okay, if I have a list of every student at Virginia Tech, then I know how many students there are. Okay, I have that part of the equation. I have the total denominator, right? I know how many students there are. And therefore, I know the likelihood if I randomly, in a probability fashion, if I go out and I randomly select 100 students, I know that what percentage chance every single one of those students has of being selected, whether it's 1 in 10,000, 1 in whatever it is, 1 in 20,000, because I know the denominator of that fraction. In some cases, we don't know the total number of the population. We don't have a sampling frame. And therefore, the reason why it's called non-probability is I cannot say with any certainty the likelihood of selecting this particular person to be in my sample, this particular element from the larger population. And there are a couple of examples here of non-probability sampling methods. The first is good old-fashioned availability, which is also called convenience sampling. This is where you simply, it's sometimes called haphazard, accidental, or convenient sampling, right? The idea is that you're just going to grab whoever you can. I might go walk out on the drill field on any given day and just stop anybody who's walking by, right? It's known as haphazard or accidental because there's just the likelihood is just completely random of someone being selected, but your population is not being equally represented in most cases. It's very risky to assume that the results can be generalized. It actually masquerades as a more rigorous research method related to numbers. So, for example, magazines used to send out surveys. They would query their readers and they would tabulate and interpret that data with a large sample size based upon their circulation numbers, but only a fraction of readers submitted those questionnaires back, and there might be something very unique about the people that choose to take the time to do that. So a sample that is drawn through availability methods is really generally not thought to be representative, and we have to be very careful about how we generalize from it. Another is known as quota sampling, and this is where we don't know we don't know every single individual unit within the population. We don't have a true sampling frame, but we do know certain percentage characteristics about it in proportion to their prevalence in the population. So if I didn't have a list of every Virginia Tech student, but based upon previous demographic research, I knew that it was 55% female, 40% male, and then some difference of people who identify as neither. If I knew that it was broken down into socioeconomic status in a certain fashion based upon forms you have to fill out related to student aid, that kind of thing. I might know certain characteristics as a percentage. I might know the prevalence of them in the population. And I might go about trying to ensure that my sample had a similar proportion of that particular characteristic. If I'm looking at a group, and again, I apologize, I always come back to gender because it's an old-fashioned, simple way of thinking. I truly appreciate that it does exist upon a continuum, but for the sake of this argument, if I know that my population generally breaks down as 55% female, 45% male, using that antiquated dichotomy, right? I can draw a sample in a non-probability way, but just make sure that my sample is 55% female, 45% male. And this is especially relevant if I think gender is important in the thing that I'm studying, right? If I don't, then it may not be that important. But it avoids some of the potential problems of the sort of more haphazard, convenient sampling approach. Another is a non-probability technique called purposive sampling. This is one in which we are really drawing a specific individual element because they have unique characteristics or position. Very limited generalizability to an at-large population, but sometimes this makes sense. If I am doing some research, on opinions about COVID-19, and I'm particularly interested in what epidemiologists have to say, knowing that there are only so many epidemiologists in the world, right? It's not a hugely popular profession. I might specifically seek out epidemiologist as the sample elements that I'm looking for, and I might do it in a non-probability way. I might just send emails to as many as I can find listings for online and see who responds. Limited generalizability to, say, Americans or human beings on the planet, but it's purposive because I'm really only interested in epidemiologists in this case. So these are the three basic non-probability methods that we use. So these are a few examples of quota sampling. This is an image from your book. So again, if I'm looking at this population utilizing a dichotomous view of gender, and I have 50% male, 50% female, I know that my population is 70% identifies as white or Caucasian, 30% as Black or African American. I can at least make sure the sample I draw fits those characteristics. Now, this quota sample on the right is only utilizing the quota of gender, right? I'm not maybe necessarily sampling based on race. So what I get is a representative sample based on gender distribution in my population, but not representative of race. Now, if I'm not concerned about race, if I don't think that it's a relevant factor for what I'm studying, no big deal. But if gender is, then this is significant. So a quota sample has to pick which characteristics to use as your quota. And as you can imagine, there's only so many axes that can be crossed here before it gets too difficult to find enough people to fit those characteristics. So usually you stick to characteristics about the population that are relevant to what it is you're studying, or at least your theory tells you they might be relevant to what it is you're doing.